first of all, good morning, Supriyo. Mr. Supriyo Ganguly graduated from BE College in the year of 1994 from our own department, Metallurgical Science. Then, after he graduated from our college, he joined Tusa Martin, and then later he joined to Tata Steel. And then he decided to pursue his career for higher studies. He went for his PhD and then postdoc from UK in Manchester University. Presently, he's working as a reader in Cranfield University, and his strong domain is on laser welding and laser joining. And I don't want to spend more time to introduce him. So over to you, Supriyo. Thank you.
Thank you, Sukamal, and thank you to the team Reminiscence for giving me this fantastic opportunity to present before you all. And it is and I'm really humbled for this, and I'm really honored. Okay, I will start on this presentation because I want to speak on the application of laser. Actually, since I joined Cranfield, I have I received some grant and funding from the Engineering and Physical Sciences Research Council in UK, and also some from industries, and on which I've done some work in the area of laser welding and how it can be a very high productivity process, and also for some advanced joining applications. And I will just talk to you on this journey of mine during the last about 8 years. So before I start, I will just give you a brief introduction to Cranfield University. I mean, not of the university, but mainly about our center within the university, which is known as Welding Engineering and Laser Processing Center. I will give you a context about why laser welding could be an option or could complement the other joining options in a technologically sound way. And the last point I will talk to you about my own research in the area of dissimilar joining. And this is particularly, it happened to be in the area of transport, but it doesn't really prevent from any other areas. And currently it is in the e-mobility sector, where battery joining and stuffs are extremely important, and laser is used as a flexible and as a very high productivity heat source for such application. And I will then talk a little bit about hybrid laser arc weldings, and this is for another domain of laser where we join very thick structurals, say for oil and gas or other civil engineering and all. So that part will be covered in that. So I will just give you a brief on the different work that we are doing in this area. Okay, so Cranfield University, you all know where is UK. So Cranfield University is located about 50 miles north of London, and it is like bisecting Cambridge and Oxford in a line between them. So it is located in this area. So we have a very greenfield kind of an area where you can't do much except probably concentrate on your studies, and this is why people we try to show this proximity of Cranfield to London, so that you can have some enjoyment while you are there. So this is this picture, this aerial view were taken a few years back. This within the red rectangle you can see the building, so which I will just show in a few minutes, slightly more details. And we call ourselves Welding Engineering and Laser Processing Center, and we were founded in 1961. At the moment we have over 600 alumni. So Cranfield is a postgraduate university, so we do only masters and PhD. At the moment we have about 8 academic staff. Actually, we have increased by another one in the last few years, and then we have about 3 technicians, on an average about 10 to 12 postdoctoral research fellows, about 15 PhD students, and about 16 full-time equivalent students. So we deliver this course in both full-time and part-time options. So I will just show you a small video about our lab. Hi, Sukamal.
Hi, Supriyo.
Hi. You know, it's continuously people are admitting here and it is coming up on the screen. So can this be avoided, because it's very difficult to speak when it comes up on the screen, if possible.
Okay, let me check. Yeah. Sorry for that.
No, I'm just saying. Okay, this video will show you a brief about our center. So this is done by one of our students, by taking a photography on, this videography on a drone that he has, and this is our center in a closer look. So you can see is a car park, and this is the lab. So what I want to impress on you is the scale of structures and stuff that we can do here. So this is a truly a kind of advanced manufacturing center. So this is, as the name suggests, Welding Engineering and Laser Processing Center. So these are the laser labs. So we have all the advanced welding tools. So these are lasers. So we have laser not only for welding, but also for pinning, cutting, and all those different applications. And additionally, we do a lot of industrial funded projects, but our approach is extremely fundamental. So if you go about our research portfolio, you will see about 60 to 70% of the money is coming from research councils, and about 40% from industrial work. So basically, we want to have a very good understanding on the fundamental and underpinning science, and then use it for specific applications or a range of applications. So the research overview is we have three main wings of research, which is additive manufacturing, laser processing, and novel joining solutions. So these are the three main activities that we have, and they're underpinned by process modeling. I will talk mainly about laser processing or laser joining in this particular session, but I will just give you a quick view of the I don't know why this video is not working. So anyway, so this is wear plus arc additive manufacturing. So this is one of the major activity at the moment in our center, and in this particular mode of additive manufacturing, we are internationally leading by quite a margin, basically. So I don't know why this is not working. On the right hand side, you see this one is a plasma arc source, and in this area we show that these are always automated processes that to create a robot and as a manipulation source and create a structure. So this particular structure is basically for use in the gearbox in an aircraft. So these are all made of titanium, and this particular process is incredibly important so that you can obtain a very good yield of titanium when you apply it for aircraft applications. So this is one of the major area of research. Although I'm not going to talk about this, I thought it will be important just to show a slide of this. So what I'm going to talk is basically, as I said in the as a part of the context, so why we use laser joining. So the advantages are it is very highly adjustable, and you can obtain very high power density, which gives you higher productivity, less damage to parent metal because you have the heat input quite low, because you can really weld very fast. And that will give you the other benefit of having lower distortion and thereby lower thermal stresses, residual stresses, and everything. And the other big advantage is the flexibility in the spatial and temporal resolution in applications. So what does it mean by this is you can have a laser beam on for a specific amount of time, and even within the time you can really vary the energy how you're applying it. And by spatially means you can add the heat to a very particular location which is very difficult in other diffused power sources, like say an arc. So this gives you the benefit of controlling the weld pool dimension very well, and also having a very good thermal profile of a weld. However, laser has a disadvantage, that is poor gap bridgeability. So this is a very important thing actually. So because when you do a joint, often it happens that the joint is not perfectly aligned. So you need your power source, or the heat that you're applying has a bridgeability or gap bridging capability, and in that laser would not be very good. So a solution could be laser together with arc. That gives you the final solution on this. So possibilities with a laser. So by this particular slide, I would like to show what are the different things, how you can apply heat at a very, in a manner that you can form the weld pool at a particular location. So you can see these are two alloys, A and B, and you can have a weld pool where you can have more of A, less of B, more of A, full of, there is something, say an interlayer X, because it is required when you have dissimilar joining. So I will explain that. And accordingly, in the metallographic constitution, you can have different composition or different phase fractions depending upon how your weld pool is formed. So basically, what I'm trying to impress on you is you can control the solidification path in order to avoid certain amount of possibilities, or you can lower the susceptibility of a system to crack. Similarly, you can have different dimensions of the weld pool. So the third one in the second row is basically, I will demonstrate you in one of my work that how I use that one. And then this is also I will show with a case study that how you can have different dimensions of weld pool, and thereby you can control the composition and also the diffusion of one parent metal into the other. So in the third one, as you will see that the weld pools are formed in all three different locations, and that is important in order to understand, or in order to prevent the diffusion of an atomic species to another, which gives you intermetallic compound formation and other problems. So as I was talking on dissimilar joining, so I will. So there are several reasons why you need to do. So this brings the topological optimization in a design. They can use the complementary properties of different alloys within a particular component. There is a very high use in transport, automobile, e-mobility sector, in health and medicine, and also in electronic sectors, particularly for battery applications in e-mobility. So I will talk about these two primarily in this particular work, in this particular presentation. So what are the challenges in dissimilar joining? So there are basic two challenges. One is the difference in physical properties, be it thermal conductivity, coefficient of thermal expansion, melting points, and all these. And the second one, which is even more complicated, is lack of solid solubility. So this leads to formation of intermetallic, which are very brittle and can cause serious damage within a weld metal. So these are some slides which show what are the problems that happens when there's a difference in physical properties. So non-uniform heat distribution, thermal stress, non-uniform composition, difference in melting point results in intermetallic formation, though is the most complicated to solve amongst these. So ways to overcome. So I will just say about physical properties, what you tend to do if, say, alloy A is joining to alloy B, and by the color I was trying to show, by the shade of the gray, I'm trying to show that that there is a difference in physical properties. So what you do, you add an intermetallic, or you add a buttering layer between them, and then once you machine them, you can then create the joint, and thus you try to avoid any kind of problem of, say, thermal stressing, bending, and all those kind of things, even solidification cracking. Intermetallic though is a different thing. So this particular work, which I will show it slightly more details, the top part of this is a steel and the bottom bit is aluminium. And here you see in the interface, we formed this brown, this layer, which I am now showing by my mouse, is basically intermetallic compound that has formed in the interface. So how we join this? We put laser on top of this. As you can see, here is a small melt pool of steel, but we try to control the heat in a manner that the heat will conduct through the steel to the aluminium, and this aluminium is now molten, and at the interface, the aluminium wets the steel. And this way, you can prevent an intermixing of steel and aluminium, and that will prevent formation of tremendous amount of intermetallic compound, which will make the joint practically unviable. Now, this is another graph which basically shows that how the tensile shear strength, which is on the y-axis, is changing or is varying with the intermetallic layer thickness. Now, as you can see, at a lower thickness also you can have a lower strength of a joint, and that is because it not only depends on the intermetallic amount or volume, but also on the total amount of weighted area. And that is basically studied in this particular research, and we try to form the solution for joining of aluminium to steel. So what are the possibilities when it comes to intermetallic? So when you join a compound, an alloy with another alloy, say an alloy A with alloy B, it can be perfectly fine. They can have a nice solid solubility amongst each other, and you have no issue of joining. Similarly, you can have a scenario which is like this, which basically shows practically there is no solubility at room temperature between these two alloys, and that will give you excessive intermetallics, which will make a joint liable to fail. Now, this will not work. So what is the option? So you can have another interlayer, which is C. You have to ensure that A goes well with C, B goes well with C, and therefore you can make a joint. However, it might happen that both of them do not go well with C. Say B doesn't go well with C. I mean, B doesn't have any solid solubility. Then you might have to introduce another interlayer, and that will give you the solution. And now I will show you with some type of with some work that I have done how this was possible. So laser is the only power source that can be used for such type of application, as it gives you the required spatial and temporal resolution, and understanding laser metal interaction parameters and ability to control the melt pool composition in a specific and desired pattern. So these are the two reasons why laser will be practically the most appropriate solution when you form such joints. Faster thermal cycle also is another great point, because as I said that the heat can be applied, the heat input for laser welding is much lower. That gives a very good thermal cycle, and which will help in diffusion of atoms and forming larger volume of intermetallics. So I will now just explain very quickly some of the fundamental parameters with laser metal interaction. So as you see, that this is a laser beam, and the spot size of the laser, say, is d, the diameter. Then what we see in a machine is laser power, the travel speed, and the spot size. But when we try to convert them, what the metal is seeing is basically power density, the interaction time, which is demonstrated by this small animation, and then the total specific point energy that is applied on a joint. So you need to understand a process from that perspective in order to make it suitable, and also so that you can do work in different lasers, because this D normally changes with different lasers, and that is a important thing for you to appreciate. So there is an example of a paper which is published from our department. It is in the area of the basic laser metal interaction. So some applications now. As I said, that you can have a scenario where you conduct the heat from steel to aluminium, because the conductivity of aluminium is much higher as compared to steel. And you can always use here copper backing bar. So the heat is conducted from steel to aluminium, and you principally avoid melting, creation of a fusion zone with all molten steel and molten aluminium, because that will be catastrophic in terms of intermetallic formation. And you can see nicely the difference in the melting point of them, both of them, and that gives you the basic possibility to create such joint. However, you can see here, this is the actual macro of that, and here at the top, it is molten. The steel is about 2 millimeter thick. Now you can see here this molten steel at the top, so you really cannot create a gradient where at the interface aluminium will be molten, which is basically means 660 degrees centigrade is the pure aluminium. But for aluminium alloys it might be 550 and all. And here is steel, which is roughly 1470, 80 like that. So you can see you can create a kind of a thermal gradient that will allow aluminium to molten at the interface and wet the steel. And based on the thing, you can then study the intermetallic formation in the different part. So now this slide is basically trying to show you how the power density and the interaction time helps in forming intermetallic. So I will not go through in great detail with you, but with very controlled experimentation, we've tried to decipher what is the weightage that should be given to power density and to interaction time in intermetallic formation. I will just draw your attention to this point 2, where you will see that the intermetallic layer thickness is quite small or low as compared to the other. So this is kind of best. However, the tensile shear strength is very poor, and this is because the bonding area is poor. So it is not only the intermetallic that decides everything, but also how much bonding area you have. And this particular combination was found in this work and explained in this particular article, which is written by my student Sonia. And one of the example is in the Shear Hull structure, where presently this kind of a composite bar is used. So this is explosion bonded. So this is steel, this is aluminium, and this is explosive bonded bar. And the steel part is joined to the steel part and the aluminium part to the aluminium part. And this, as you can imagine, increases the cost for manufacturing this kind of structures a lot, because you need to have a bar, which is expensive, and then you need to have 4 weldings, whereas you can done with normally 2 arc weldings. So what we proposed is a structure like this. So this is steel and aluminium should go inside, and when laser comes like this, so see, a design modification was required in order to make the thing suitable for a specific application. And then the heat should pass through the steel and form this joint with here. And this is done by using a setup in our lab, and this basically this is kind of a T-joint that is formed at the end of this particular process. And therefore, what I was trying to say is, indeed, it will be possible to use or apply laser in an intelligent manner, and then to modify the design of a structure in order to create a joint. Okay, so these are the particular examples of how laser can be suitable for such thick structures. Another example of this another example is microjoining. This I will talk about joining of stainless steel to nitinol. So nitinol is a shape memory alloy. I'm not sure whether you are aware of nitinol. So it's a shape memory alloy, and it has very good application in dentistry as well as in other medical applications, and often it needs to be joined to stainless steel. So the problem here is serious, because stainless steel contains iron atom, and nitinol contains titanium atoms. So nitinol is basically 50 atomic percent of nickel and titanium. So titanium and iron are a no-no situation. They just, not only they cannot form solid solution, but the intermediates that they form are absolutely brittle, and you cannot form a viable joint with iron and titanium. So study was done in our center, as I said, to understand how that we can form joints. If you recall my previous schematic explanation, in the same way, we use two different interlayers. One is vanadium, the other is niobium. So vanadium is good with stainless steel, and niobium is good with nitinol, and vanadium and niobium are good with each other. So, but if you form a weld like this, then what happens? You really completely cracked it. And the reason being, the atoms of titanium can travel through this melt pool and form this intermediate on the other side. However, if you do separate welds between vanadium and stainless steel, niobium and nitinol, and then with vanadium and niobium, then it is possible to achieve. So this was subjected to very strong testing basically, and you see here the breakage happens from the nitinol side. So basically the weld metal is okay. So if you understand the reason why something is cracking, and then take necessary design precautions in manufacturing or manufacturing design precautions, then most likely you will be able to achieve a good solution towards the end. Okay, so this is the other example. Now I will talk a little bit about pulse laser, and I just like to show that this is the interaction time, which is a infinitesimal spot experiences when the spot passes over, but here it is not continuous. So here it applied with a particular frequency in a second, and therefore the interaction time would not only depend on the size of the beam and the velocity, but also on the frequency. And this is the formula of converting frequency with overlap factor. And here I tried to show how different overlap factor can be effectively built into the interaction time calculations, and that helps in getting a proper understanding of how much heat is actually applied in a particular situation. So I will now talk about some applications, some battery applications actually in new mobility. So where I would talk about joining of copper and steel. So the latest generation fiber lasers, they offer very high flexibility and a range of pulse profile and duration. Pulse energy and average power can be controlled very well. Short pulse duration are ideal for fast freezing, so which is important for dissimilar joining. Very high repetition rates, so you can actually have a reasonably high peak power and a reasonably high average power, and it gives you very stable processing. So all these factors actually made it a very good tool for dissimilar jointing. So this is an application of dissimilar joining, as you can see here. So these are characteristics of the laser where up to a certain amount of pulse frequency, the energy is constant. Further increase in pulse frequency will cause the pulse energy to drop, whereas the power will keep on increasing, and power is basically energy divided by the time. So at the lower frequency, the power keeps on goes up, and then over a certain frequency, it remains constant. And this is an expression of how the energy applied, maximum energy in a particular laser. So with the help of a cathode ray oscilloscope, we basically deciphered how the different pulses behave and act before we apply them. So this particular graph basically is showing how the energy per pulse changes with the average power. Similarly, as we go along, so this shows that how for two different average power output, how the peak power output changes. And you see here, the time duration of the pulse remains same. Similarly, in the next one, it is the time duration is changing while the peak power is almost kept constant. So what I'm trying to basically convey is the temporal resolution or time-dependent application of the energy can be controlled to a very high level in such laser. So this is a work which is done for joining of copper to steel, stainless steel. And you see this is the overlap. Sorry, this is not stainless steel, it's copper to aluminium. And you can see here the experimental setup which was used in the lab, and we used a galvo scanner because the laser needs to be moved very, very fast. And there's the copper backing bar that we have used in this particular application. So quickly, just a very structured analysis was taken. So aluminium of 0.5 and a copper of 0.5 was first studied. So as a bead on plate, just to see how much is the penetration happens. And then actually aluminium 0.25 and two aluminium 0.25 millimeter were tested. Similarly with copper, and then aluminium and copper were tested as a dissimilar jointing. So to understand how the heat flows between the different joints. So in the bead on plate result, as you can see, for the same application of energy, you get much higher penetration in aluminium as compared to copper, which is not surprising because copper is highly conductive and the temperature rise is rather slow in copper as compared to aluminium. And here this graph basically shows for the same type of waveform how the two alloys respond to the heat. So now here you can see here this is 0.5 millimeter aluminium and this is 0.5 millimeter copper and this is 2.25. So the interesting thing is we all thought that this one will give you much higher penetration as compared to this, but it was not to be the true. As you can see in the next slide, the penetration of 2.25 millimeter parent is higher than the bead on plate of 0.5 millimeter, and the reason behind this is the gap between the two sheets is basically allows the keyhole to propagate faster. So this is really interesting because we always think that an integrated joint or say when we do 2.5 millimeter will always give you better penetration because of the heat sink that it will provide. Anyway, so this is the two configurations. So aluminium on top and copper on top, and as you can clearly see that the weld formation is much better when copper is on the top. And the reason being, in this particular configuration, when aluminium is on the top, the heat formation was, the joint formation was not contributed by copper at all by much. But here, the copper penetrates well within the aluminium when it is being irradiated. So you will see now from the EDS curves that when copper is on the top, it really gives you very well penetration of aluminium, and copper also penetrated significantly in the aluminium, whereas in the other case, there was not much penetration of copper to the aluminium, and therefore the joint formation was not very strong, although it was not seen that much by the mechanical strength, but that was what was found from the EDS analysis. So these are some elemental mapping through the joint, and as you can see here, when copper is on the top, in this part you have significant penetration of copper, which makes the joint very sound, whereas when aluminium on the top, aluminium didn't penetrate at all in the copper bit, and that is what is the problem. This is the mechanical strength of the joints that we formed, and both the joints actually gave very similar strength, but on macro, as I just shown, that the macro of copper to aluminium looks much better as compared to the other way around. So now I have said about laser for dissimilar application. Now I will just quickly browse to some slides on higher productivity, and this is for real structures like say oil and gas and other. And you will see how hybrid laser welding can be an important tool in getting some high productivity jointing in thick structures. So laser on its own is can penetrate well, can give high productivity, low distortion, narrow heat affected zone, and all those stuff, high precision. But it is expensive, poor fit up, and the cooling rate is very high, which is not very desirable in some steel structures, particularly when the carbon equivalent is high. But with arc, it gives you, it is kind of complementary. It gives you good fit up, relatively cheap. It is well known. I mean, people know about these processes a lot. However, it gives you more distortion and it is a bit slow. So if you can join them, it can give you the benefits of both the processes together. And that is what I will show you in this hybrid experimental work. So the thing is, why hybrid is important is when you join two pipes. Generally, pipes are nowadays produced by thermomechanically controlled steel. They do not have any alloying or very minor alloying, and the strength comes from the mechanical processing in the mills or while cold rolling and stuff. So when we do a weld, then the steel will be molten and they will be joined by the same parent metal. The flip side is it will lose all of its strength because it is molten. So we need to add some filler wear. So importance is when you form a joint in structurals, then not only you should penetrate, but also you should be able to add filler wears, which will give you, say, solid solution strengthening elements in order to form a proper joint. Here are some examples which was done by previous researchers. So multipass GMAW welds. It is very good, but it is quite slow. The heat inputs high and stuff. This is pure laser weld. However, this part will be incredibly weak because it is molten parent alloy and didn't have any strength whatsoever, and it might have even a martensitic structure or something because of the higher cooling rate in the heat affected area. And this is a hybrid weld. So you can have a filler metal deposited. However, the point is it only deposition good, but the filler metal needs to penetrate. So practically you need to understand how the two alloys or how the two power sources will respond or will interact with each other in order to push the filler wear through to the bottom. And this is a work that was done in our place 2 years back, and this is mainly in the area of hybrid laser arc processing. So you can see here there is a system parameters which has a speed, and then there is the weld profile. So what links them is basically fundamental parameters, material properties, which subsequently determines the thermal cycle and the cooling rate. So these all the factors needed to be controlled in order to achieve your desired weld. So here are some setups that are shown. I will not spend much time here, but you can see here, this is the kind of bevel. So these are 17mm thick steel with a 12mm bevel because you want to achieve a full penetration by laser. And X65 steels were studied. And these are some of the factors that we found when we control the power, the laser power and the wire power, and see the different weld profiles. So as you can see here, this weld was made with laser power 6 kilowatt, laser beam diameter 0.6, and the power of arc when converted is 6 kilowatt. Now, how it will manifest in a weld when you keep the laser power constant, increase the arc power, or vice versa. So filler wear. So in this particular study, we have used a duplex filler wear just to have chromium as a signature element to see how much it penetrates. So I know that it will be cracking and the weld will not be looking very good, but still we did it because otherwise it is very difficult to accurately quantify the mixing. Now in this one, as you can see, we've kept the laser power same, and with the arc power, how we can, the arc power is basically manifested in terms of the wear feed speed, and how we can change them in order to achieve a full penetration or the full penetration of the filler basically. Okay, so these are the chromium mapping or scanning of chromium using energy dispersive spectroscopy. And here you can see at a particular wear feed speed, you have a fully penetrated filler. And this is what you really need to know, I really need to decipher that for different type of power sources, how they interact in order to create a very effective joint. And also laser power can be significant in achieving the mixing. And as you can see here, with the same wear feed speed, if you increase the power, if you increase the laser power from 6.5 to 8, you can practically minimize. So what is happening in these two situations is more filler, more dilution happening with the parent, and as a result, a better weld is forming with the proper mixing of the filler with the parent. So then we try to derive this equation basically based on the understanding. So the chromium at the root and the average chromium. So basically, if this ratio is 1, then you have achieved full mixing. Would depends on this factor, which is the laser power, the voltage, and the current in a power source, the bevel size, and the speed of travel. So this type of understanding will help you in modeling a process and create a quantitative understanding of how the power sources should be controlled to achieve a fully homogenized weld. So in summary, I have to say that laser is an important tool for high productivity in automotive and other structural applications and can be useful for dissimilar joining. However, in order to realize the full potential, it is important to understand the laser feature and the corresponding laser metal interaction characteristics to apply it in a intelligent manner. And for high productivity, high thickness or large dimension structurals, laser and arc can provide a very important combination to achieve filler wear addition as well as gap bridging ability in order to realize the full potential with regards to the productivity of the process. I must acknowledge Wojtek, Sonia, and Gonzalo. So Wojtek is an academic, and Sonia and Gonzalo are now researchers. They used to be my students. Their research we all performed together, and this was shown now here. To the Engineering and Physical Sciences Research Council in UK to provide the funding for the dissimilar joining and range of industries in laser like SPA Lasers, Hirima Marine Corporations, Attica Components for funding some sponsored project, which is shown in this particular presentation. So thank you very much. I hope I'm in time. And if you have any question, please let me know.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you, sir. My voice is different. Thank you, sir, for such an insightful presentation. Now, a few questions from our curious attendees. Over to Ritam.
Hello, sir. We have a few questions for you.
Yeah.
The first question is, does laser-aided additive manufacturing have the potential to substitute welding to some extent in the near future?
Laser additive manufacturing is in existence in this world for last maybe 80 years, I think so. But laser was generally worked with powder. So if we think about direct energy deposition, which is not a powder bed basically, so you're adding powder on a laser beam. If you see that process, it is also in existence for a very long time. But generally, that process is not highly productive because of the fact that powder are more expensive and have more more variations in mechanical property as compared to wire. Now, when it comes laser plus wire, it is now in research a lot because it gives you very high resolution in creating a dimension. But laser additive manufacturing will not substitute welding because all the wrought alloys, pipes, plates and stuff will always remain in the world. So additive manufacturing is not to compete with, say, welding or joining or any other processes, but to complement, you know. So if it is a very complicated part, by using additive manufacturing, you can design it differently. You can achieve some topological optimization. You can add different materials within a component. So you can achieve all these things, but it is not a kind of a mass productive process, which cannot be replaced ever, I think. So additive manufacturing is incredibly important to create structures and design, but you need to understand the business case for that very clearly, because I mean, unless you have a proper business case, additive manufacturing might not be very useful tool.
Thank you, sir.
Yeah.
Thank you, sir. We have a second question, that is, where to focus if we are looking for a job in the welding industry?
The thing is, when you join a welding industry, you will need to focus. Basically, you see, the metallurgy should be treated as or should be studied to understand the interactions. So when you apply heat, what happens? The physical metallurgy of steel, aluminium, copper, titanium nowadays coming in a very strong manner. So you need to really grow your knowledge and understanding in this area, and that will give you a range of possibilities in everywhere. When you join an industry, it will be expected that you will have the understanding of the process. You really don't have to do it with your own hand. Although when I came out and joined industry, it was quite good to do it with your own hand, some stuff. But normally you will see within a year or 2 years. So what is the most important thing is to understand the process and to understand the resultant change in microstructures and its importance in mechanical properties of a joint or a component or anything. So once you build that understanding, you can really do what is expected from you in the industry. But if you ask me, I think personally, e-mobility sector is coming extremely seriously. And I visited India a few months back in February, and there are lots of people working in that area. And also this wear plus arc additive manufacture, which I showed at the beginning, it is also a very strong potential to employ people or good engineers in this area in future. So welding of titanium is coming up very strongly through additive manufacturing, because that gives you the potential to replace certain parts where you need where aluminium is not performing up to satisfaction because of corrosion resistance properties and all, particularly in aircraft applications. So you need titanium, and titanium is best done by additive manufacturing. So these are the areas I think. E-mobility is everyone is talking about that nowadays. So e-mobility, laser welding in that sector, because there is no other option. You need to have very high productivity welding and like some in microsecond, millisecond welding, and it is important to have laser for those kind of purposes. So all these things will probably help in an industry.
Okay, sir. We have one last question. That is, during laser ablation from the plasma cloud formed, is there any way to correlate quantum and mechanical properties and therefore predict the mechanical attributes of the alloy from this correlation.
So you're saying that when you ablate by using a laser, and can you read the question once again?
Yes, sir.
Yeah.
During laser ablation from the plasma cloud formed, is there any way to correlate quantum and mechanical properties and therefore predict the mechanical attributes of the alloy from this correlation?
Okay, so from the ablation, you're basically removing some you're vaporizing the alloy, isn't it? And this alloy is forming a plasma, and you're saying if you analyze this plasma, whether you can, and from the properties of this plasma, whether you can predict the mechanical properties of the ablated structure, if I understand this question correctly. So the point is, sorry?
Yes, sir, yes.
Yeah. So the point here is, when you ablate, you basically create a heat affected zone. Okay. Now the heat affected zone will be a heat affected zone, and it will not be dependent how it is formed. I mean, it would dependent on the thermal cycle, of course, but not whether it is done by ablation or by anything. So basically the properties of the structure will remain, or the properties of the heat affected area of the particular alloy will remain very much similar when you if you ablate. So if you know how the metal responds to the thermal cycle when it vaporizes or when it basically cools from a very high temperature, you will really know the properties of the same in that in the ablated structure. What the thing will give you, the vapor and that will come out will give you the composition of how much of the ablation has taken place. And I really do not see that whether it can be correlated to the mechanical properties. So I would think that it is much easier to understand the mechanical properties of the particular alloy if you do a simple simulation and see how the metal react with that kind of a thermal cycle, rather than you go to this complicated route of analyzing the plasma and the quantum properties and then come back to understand the mechanical properties. Does it make sense?
Yes, sir. Okay, sir. Thank you, sir.
Yeah, thank you all. Yeah.
Thank you, sir. Thank you, sir, for sharing your time. Team Reminiscence is very grateful to you for your time and consideration. We look forward to more such talks from your side. Thank you once more for such an insightful talk on laser application and advanced joints. Thank you, sir.
Thank you very much.